My topic is quantum cryptography, and in this topic we will be studying about the classical cryptography method and quantum cryptography, and also we will be seeing a case study which tells about the threats which are for quantum cryptography. So let's study about the classical and quantum. So let's begin. First is introduction to cryptography, which is basically classical cryptography. So in this we will be having a brief overview: what is cryptography, how it works, and what is the mechanism behind it. So here's a diagram which shows that the basic encryption and decryption between the two parties. So let's see this with an example. Let's say I have two person A and person B. They want to have a secure communication, so we will be having a secure channel for that, and we will be using a classical cryptography for that. So in order to make their communication secure, we will ensure that there is no eavesdropper between that. So let's say here is a person A and person B. So person A sends a data to person B. Let's say the data is X, and that data is transmitted to person B. So we have to make sure that this data is not intercepted by any other person, which is not in the communication. It is very important. Otherwise, anyone can get this data, and our communication will not be safe. So in order to ensure that, we have we use key distribution system, in which person A shares a private key to person B to decrypt the data. So what is encryption and decryption? So the person A encrypt the data at its end and shares a data with the encryption, and at the person B, the data gets decrypted with that key, and the key is only shared between the A and B. So encryption is nothing but changing the original form of the text or whatever the message is to a form which is not understood by anyone, and decrypting it at the receiver's end. So this was about the classical cryptography, but this was the overview, what we exactly how exactly encryption and decryption works. So, but how data is encrypted in classical cryptography. Let's see that. So we take help of maths here. So let's say I have a data and I have to encrypt it. Let's say I have a data X. I have to encrypt it. So we have to find an algorithm which is easy to do but hard to undo. So is there any algorithm for that? So we will be using our basic maths techniques. Like, we know that if we will multiply two numbers, let's say A and B, it will give a result Z. Let's say for now Z. So it is easy to multiply A and B and to get a result Z, but it is hard to find the factors of Z, which are A and B. So we can use this technique for the cryptography itself. How? So let's say we take very large prime number, which is, let's say, A, and very large prime number B, which gives us answer in order of some Z. These are in order of 10 raised to power 18, A and B. Similar for B. So our Z will be in around 10 raised to power 36, which is a very large number. And to decrypt it and to find the factors of Z, we have to get A and B, which is a very complex task for a classical computer. So it would take many years for a classical computer to find these factors. But so this is the problem with the classical computers, that it can't decrypt the message so easily. That's why we use classical computers. Okay, so why do we need high security? Why do we need quantum cryptography? So we need that because we know that quantum computers are very fast and they can easily decrypt this two numbers. So we already discussed that we have two numbers which are very large, and after multiplying that two numbers we get even a more large number. So this is let's go to the next PPT. Problems in classical cryptography. So the vulnerability in classical algorithm is that it is very easy for quantum cryptography or quantum computers to find these two factors. So this is a threat for classical computers or cryptography. So if we are able to make a quantum computer, it would take just few seconds to decrypt this. So what is the use of classical cryptography here? We can't use classical cryptography, and that's why we need quantum cryptography here. So let's see. So let's see how quantum computers break the encryption so easily. So there is an algorithm known as Shor's algorithm. We won't go like into that much deep, but let's understand. It is an algorithm. We have we had two numbers A and B which are big, and that gives result Z, and it is easy to find A and B in quantum computers. But how? So let's see that. Right now we are finding A. So how we can find A? We will initially make a bad guess. Let's say I have made a guess of P, and we will use Shor's algorithm to make our guess even better. So here is our Shor's algorithm. It will convert our guess into a better guess. Let's say our better guess is Q, and so our better guess is Q. So we have find Q. We don't know B, but we know Z. So it is easy. To find B. So we are successful find Q and B, which are the two numbers. So this is very easy to factorize the numbers in quantum computers. But if we will use Shor's algorithm in classical computers, it would take around 100 or 200 years to find the factors of a very large prime factors. So that's the problem in classical computers. So till now we saw that how classical cryptography can easily be broken by quantum computers. So we need a good technique to secure our data and to secure our communication, and for that we need quantum cryptography. So let's have a overview. What is quantum cryptography? How it works? Let's see. Let's say I have a person named Alice and person named Bob. This is quantum cryptography. Here they both Alice and Bob will having a polarizer with them to detect the polarization of the photon. Okay, and Alice will send photons of different polarizations to Bob. Okay, so he will be sending different photons of different he will be sending photons of different polarizations to B. Okay. So at this point Bob will catch these polarizations of electrons with his polarizer, and he will mark this polarization in his notebook. Okay. After the communication takes place, they will publicly they will compare their polarizations if they are same or not. So the polarizations which are same, they will keep those polarization for the private key, and the polarization which are not same between the Alice and Bob, they will simply reject those polarizations. So this is how, like, this is a very basic overview for a quantum, like how quantum cryptography works. Okay. So now as we got a basics of quantum cryptography and it's working. So there is a here we can see the transmission. So first phase is transmission here. So first Alice will send the random bits. Like first is 1 1 0 1. So these are the random bits sent by the Alice. Then the sending basis and Alice photon polarization. So these are the different polarization. It can be up, it can be down, or it can be in diagonal. Then once the Alice sends this random bits to Bob measures the random bits at its end by the polarizer. So these are the bits received by the Bob. Sorry. And after the transmission took place, they will have a public discussion. How? So they will be comparing the, like, what bits are same between them, like which electron have the same polarization between both Alice and Bob, and according to that they will get the outcome, and the outcome and whatever the outcome will be, it will be used as a private key. Okay. So this was about quantum cryptography and why do we need that over classical cryptography. So, but there are still some threats to quantum cryptography. Like we saw that quantum cryptography is really very secure. It can secure a transmission between two or more parties, but there can be a threat. It is not currently a threat, but it can be a threat in future. So for understanding that, we will first see no cloning theorem. So let's see the no cloning theorem first. So what is no cloning theorem? So we know that there were two persons, Alice and Bob. They were sharing data between their both, and they were sharing and they were using quantum cryptography for that. Okay. So let's consider an example. There is a eavesdropper here in between, which is trying to access the data which is shared between the Alice and Bob. So if a eavesdropper try to access the data, accessing the data means he will access the photons. Okay, like he will for accessing the data, he will need to know the state of the photon, and we know that for knowing the state of the photon, we have to destroy the state of the photon for that. So if this guy try to access the data, he will destroy the state of the photon, and this thing will be noticed by Bob, and he will know that someone is trying to access the data. So it is a failure. That so at this point we can know that, like, it is very obvious that in quantum cryptography it is really very hard to know what data is being shared between the two parties. Okay. So the best point is, if a thief or eavesdropper want to access the data, he have to destroy the state of the particle. This is the point. So this is nothing but the no cloning theorem. If we want to access a data, we have to destroy the state of the electron in order to access the data. This is nothing but no cloning theorem. Okay. So but what if there is a way that we can we can still overcome this? How? So there is a way which is not very advanced right now, but that this can be a potential threat. So it is known as non-demolition technique. So what is non-demolition technique? In this technique, we are actually, there were two persons, Alice and Bob. They were having a communication between them. A eavesdropper come to access the data. He destroy the state of the photon, which is known by the third person. So to overcome this, there is a technique known as non-demolition technique. In this technique, the eavesdropper or the person who is trying to access the data unauthorizedly, he can use this technique to get the to get the information of the photon without destroying the state of the photon. Like this is really a very, like this is not very advanced right now, but if there is any discoveries in these topics, it can be a possible threat to quantum cryptography because we are not actually destroying the state, we are accessing the data without actually destroying the state of the photon. So this can be a possible threat to quantum cryptography. So this was the case study on threats to quantum cryptography, in which we have studied the no cloning theorem and non-demolition technique. Thank you.